not so far.
Right. Okay, so yeah, thank you for the invitation. It's great to be here. So I'm going to be talking about how detectable gravitational wave signals may arise from beyond the standard model physics. And I'll focus on an example in the context of string theory that we studied in this work, in this paper here, where we in fact argue that in the context of string theory, you may in fact expect a lot of gravitational wave signals of wildly different frequencies. So something like the string soundscape. Right, so as you all know, gravitational waves are a prediction of GR. As a gravitational wave passes by, it causes matter to squeeze and stretch in this way. And this relative amount of stretching and squeezing is what we call the strain of the wave. So here, h2, which is basically just the amplitude of the wave. So even though this strain may have been a very large number at the point where the gravitational wave was first produced, it falls like 1 over the distance for a point source. So once it reaches us here on Earth, this may be a very small number. And so gravity wave detectors are precisely designed to detect these very tiny strains caused by an incoming gravitational wave. So it's useful to think about the energy in gravitational wave as well as their strain. So for instance, in the weak field limit of GR, it is possible to build an object, this C mu, which we can write in this way, which would basically correspond to the stress energy tensor in gravitational radiation. And here we're just writing it in a particular gauge, so this transverse radius gauge. But basically, so the idea is the not component of this tensor will tell us about the energy density in gravitational radiation. And if I normalize this energy density to the critical energy density of the universe, then we find out that actually this scales like the frequency square of the wave times the strain square of the wave. So obviously more frequency, more energy, more strain, more energy. However, it's worth noticing though that for a given energy density in gravitational waves, waves with higher frequency will produce smaller strains. And this is the reason why it is so hard experimentally to build competitive detectors at very high frequencies. Because for a given energy density, you need to be sensitive to smaller strains. I'll mention this later again. Yeah, so as we all know, this is a very exciting time for gravitational wave astronomy after the first direct detection by LIGO. And in the future, there will be many more detectors that will do so as well at very different frequencies. So obviously, this is going to be very exciting for both astrophysics and cosmology. And detections at different frequency will tell us in the coming years a lot of things about a whole different population of astrophysical objects. Right, so this is a plot of the sensitivity curves of a few gravity wave experiments. So in terms of the strain, they can detect as a function of frequency. So for instance, LIGO, as you all know, operates between 10 and 10 to the 4 Hz, and has a peak sensitivity of around 10 to the minus 21. eLISA, which hopefully will be operating not very long from now, will be operating in the 10 to the minus 5 to 1 Hz region. Then there is this Big Bang Observer project, which is very long in the future, but hopefully it will be covering the frequency range in between. And then in the very low frequency regime, we have the pulsar timing array observatories. Both the EPTA, which is already operating, and SKA, which is an upcoming project. Right, so this is how well the detectors can do, and this is how some of the astrophysical signals are expected to look like. So for example, this red patch here corresponds to the first signal that LIGO discovered. And then other astrophysical signals involve in spirals, so binary spiral systems of different types, also supernova explosions. And here at the low frequency range, it's mostly, the main source is thought to be just supermassive black hole binaries. So it's useful to look at this plot actually in terms of the energy density. So as I said before, the energy density is related to the strain as strain squared times frequency squared. So this plot actually looks a little bit different when we plot it in terms of the energy density as a function of frequency. And here is where you can appreciate that even though LIGO has, one of the best strain sensitivities, actually in terms of the energy density in gravity waves, it can detect. Because it's operating at such high frequencies, it's nowhere near as good as the PTAs or eLISA will be. And this is why, as I said, it's like so hard to fill the region here with another competitive experiment. Right, so this is obviously very exciting, both for astrophysics and cosmology. But here we'll focus on the question of whether we can also use these types of experiments to learn something about beyond the standard model physics. So the answer to this question is surely yes, and then there are already a few examples, but this is mostly an exploratory territory, say, by collider standards, certainly. So obviously, most famously, there's the possibility of stochastic background or gravitational waves, maybe from some kind of inflationary dynamics. Another very well-motivated example is the possibility of having a strong first-order electroweak phase transition, maybe linked to the generation of invariant symmetry. And this could be perfect, actually, for ELISA, because this could correspond to a gravity wave signal in the millihertz range. And then another example is the possibility of probing the existence of axions. Here I said the QCD action, but it applies more generally for light scalar fields due to black hole superradiance. And this could be even be relevant for LIGO. So there are a few examples, but here in this talk we'll focus on the possibility of producing gravitational waves arising from a process of vacuum decay that happens at zero temperature in a string theory motivated scenario. So just two comments before we move on. So many of the things I'll say actually apply more generally to theories that have hidden sectors, irrespective of string theory. And then I also want you to keep in mind that, so we're talking about the process of vacuum decay that happens purely through quantum tunneling. So this is not going to be a first-order thermal phase transition. There are many things that are similar between these two processes, but there are also many things that are different, as I will point out. Right, so before we continue, I need to tell you some things about string theory. As you know, string theory is consistently formulated in 10D. So there are 6 extra spatial dimensions that need to be compactified. And the typical compactifications we're going to focus on look something like this. So there is some bulk region, which is mostly unworked. So the internal space is mostly flat. And then there are typically very many regions, which are the spikes here, of very high gravitational working, which are called throats. So if you are not very familiar with this, it's useful to think of these throats as just some Randall-Sundrum throat. So you should think of this, the part of the throat that attaches to the bulk as the UV part. And then you should think of the tip of the throat as the position of the infrared brain. Okay, so why do these throats appear at all? So it turns out that string theory contains higher form generalizations of abelian gauge fields and their field strength. So it would be like the F mu of electromagnetism, but just with more indices. Here we will only focus on 2 such field strengths, so these 3 form fields. But just as in electromagnetism, we have electric and magnetic fluxes, we can also have fluxes for these fields. And it turns out that actually it was found out that these fluxes actually play a very important role in string compactifications. So just as in electromagnetism, these fluxes carry an energy density, therefore they gravitate. And in fact, these highly warped regions, these throats, actually arise as a back reaction from these fluxes on the geometry. So more in particular, what I mean is, so if we focus on the tip region of one of these throats, we can find out how much flux goes through these throats by integrating these 3 form fields over some suitable 3-dimensional surface, with here are these 3 cycles. And the amount of flux will be just characterized by some integer numbers that here we call m and k. So each one of these throats will have some amount of flux characterized by these 2 integer numbers. And the statement that these throats appear as a back reaction from the fluxes, actually what it means is, so the warp factor at the tip of the throat is given by this expression. So it depends exponentially on what the values of these fluxes are. Okay? So, yeah, so the amount of flux, so in principle all these throats will have some amount of flux going through them, but it doesn't have to be the same amount of flux. So you should think of the flux as you change from one throat to another. This could change by an order 1 number, but notice that changing the flux by an order 1 number basically means changing the warp factor by a huge amount, right? Since it depends exponentially. So you should think of this picture as a picture of very many throats, in which the characteristic IR energy scale of each throat varies wildly as you change from throat to throat. Okay? Right, so degrees of freedom can be localized anywhere on this compactification. So for instance, the visible standard model sector could be localized somewhere in the bulk, or it could be localized somewhere at the tip of one of these throats. And similarly with other degrees of freedom that may not be interacting with us. So basically, the message I'm trying to get across is that this kind of a scenario motivates a picture in which the standard model coexists with very many hidden sectors that may be living at the tip of these throats, and that have a characteristic energy scale that is very different as you go from one throat to another. And these hidden sectors may be interacting very weakly with us. In some cases, maybe just only gravitationally.
Question?
Yeah.
Just to go back to something very basic. This is a picture of the compactification of the extra 6 dimensions.
Yes.
This is attached to our 4 dimensions.
Yes, yes. So you should think of this as just like, so our 4 dimensions, so the standard model would be just like a point.
Okay.
4 dimensions here in this picture, yeah.
Okay.
Good. Yeah, so one example of degrees of freedom that can be localized are D-branes. So D-branes are non-perturbative objects that arise in string theory, and they have D spatial dimensions. In particular, a typical one of these throats, normally you can find it having a few anti-D3 branes. So anti-D3 branes are just a particular type of branes, and normally you'll find these localized at the tip of the throats, and in the presence of some flux background, this will break supersymmetry locally in the throat. However, so the authors of this paper studied the physics of throats with anti-D3 branes on them, and they found that the situation is actually unstable. There's always a stable vacuum, like a true deeper vacuum, in which there are no anti-D3 branes and supersymmetry is preserved. So in particular, they found that the leading effective Lagrangian that describes this system is an effective Lagrangian of only one scalar field. And notice, so there are 2 things I want you to notice here. So this scalar field has some weird looking kinetic terms that I'll focus on, I'll mention later more. But basically, the effective potential is basically just controlled by a single parameter, which is this P over M ratio. P here is going to be the number of anti-D3 branes on my throat, and M is just, if you remember, like one of the fluxes we have. And in particular, they found that there is a critical value of this parameter, which is around 8%, such that for smaller values of P over M, this metastable vacuum I was talking about appears, as well as a true vacuum, whereas for larger values, there is no metastable vacuum, so it's just, the system is just classically unstable. Okay, so this picture is a picture of what I just said. So this is the effective potential of our scalar field that is describing the physics of the throat. So if this ratio is bigger than 8%, then there is just one true vacuum, and if you are found here, then you will just roll down classically down the potential. As you take this ratio smaller, then a second metastable vacuum appears. And as you take it smaller and smaller, then it will just become deeper and deeper, and this metastable vacuum will be just longer lived. But yeah, so the idea is that for smaller values of P over M, there is a metastable vacuum in which supersymmetry is broken, and a true deeper vacuum in which it's not. And then your metastable vacuum will be unstable under quantum tunneling to the true one. Okay, so the authors of Casio, Christian, and Berlin, they focus on this system in the case where P over M was very tiny. We are going to focus on this system in the regime in which we are very close to the critical situation. So we will be very close to the situation in which this barrier is disappearing. And we introduce this parameter delta just to characterize the sort of fractional deviation from the critical case. And we'll take delta to be much smaller than 1, in which case we'll find that the lifetime of this metastable vacuum might be of cosmological interest, as I'll say later. But the question we're trying to answer is whether gravitational waves produced from this vacuum transition could be strong enough to ever be detected. Okay, so before we move on, so we need to make some simplifying assumptions. So we will assume that once inflation is over, there is at least one of these throats that is in this metastable vacuum I've described. We'll assume also that, so after inflation, our visible standard model sector is reheated up to pre-BBN temperature, so BBN happens undisrupted. But we'll assume that the hidden sector that lives in the throat is reheated to much smaller energies. So effectively, a zero temperature treatment will be enough. And so, as I said before, the decay will occur via quantum tunneling, not thermally. And the final assumption will be that the early universe will always be radiation dominated. So at any given time, the total energy density will have a contribution from the thermal energy density of the visible sector as usual, but there will also be a vacuum energy density from our metastable vacuum. And the assumption is that this ratio is always going to be smaller than 1. So the universe is always radiation dominated after inflation. Okay, so the picture of what's going on is the following. So once inflation is over, our throat is stuck in this metastable vacuum, and it will remain there until the probability of nucleating a bubble of true vacuum becomes of order 1. So the probability of nucleating a bubble of true vacuum in a Hubble time, in a Hubble volume, is given by this ratio. So this is just the decay rate per unit volume, and this only depends on the details of the throat. It's a quantity that doesn't depend on temperature, and this is divided by Hubble to the 4th, which, as you know, becomes smaller as the temperature drops. So this is a quantity that, as the temperature of the visible sector is dropping, is becoming bigger. At some point, this will become order 1, which is when the transition will start. And then shortly after, once it's completed, then the throat will find itself in the true vacuum. Okay? Yeah, so just in pictures, what I've said is this. So there's some nucleation temperature in which you start nucleating bubbles. These bubbles will start expanding very quickly. They're quickly approach the speed of light. While they are expanding, because the situation is spherical, they won't be emitting any gravitational waves. But then at some point later, they will collide, and here there will be a certain amount of gravitational wave emission. And then finally, the transition will be over. Okay. Right, so in order to know at what temperature your transition is happening, you need to compute this nucleation probability. And so you need to know the decay rate of this false vacuum. So the way to compute this is basically just to ask what is the energy of this false vacuum. So you can try to compute the expectation value of this operator in the false vacuum state. So h hat is just a Hamiltonian operator, tau is real. And one way to compute this is to use the usual Euclidean path integral formulation approach, in which here in this right-hand side you're summing over all paths that start an n in the false vacuum. And of course, as usual, this is just the sum is going to be dominated by those field configurations that extremize the Euclidean action. So you're looking for solutions that extremize this guy and are subject to these boundary conditions. So R is just so notice that this equation is of 4 symmetric. The solution will be 2, and here R is just the of 4 symmetric radius. So the boundary condition is just that for large R, the value of psi goes to the false vacuum. So for instance, if you have a vacuum, if you have a potential that has just one minimum, then the only solution to this equation with this boundary condition is the trivial solution, psi equals false vacuum. And then you find that this guy is just a real number, which corresponds to the energy of the false vacuum, and that makes sense because if you only have one minimum, that state is an eigenstate of the Hamiltonian. However, if you have a more interesting potential, perhaps with 2 minima, that's no longer true, and in particular, you'll be able to find another solution to this guy that is non-trivial, and that's what people normally call the bound solution, okay? So in our case, this equation, which is also known as typically the bounds equation, looks like this. And as I said, so this bound solution, psi b, is the one non-trivial field configuration that extremizes Euclidean action. And in particular, it contributes to what would be the energy of the false vacuum in this way. So it depends, notice, it depends exponentially on what the value of the Euclidean action is evaluated at the bounds. This is just a numerical factor, it doesn't matter much. And then there is the determinant of this operator here, the second variational derivative of the action at the bounds. And it was noted crucially by Coleman a long time ago that it's a crucial characteristic of this bound solution that this operator has one and only one negative eigenvalue. So if this operator has one negative eigenvalue, when you take the square root, you get the factor y. So you'll get a contribution to your energy that has a factor y that you can interpret as a decay rate. So basically at the end, so this is how you compute the decay rate. In the end, it's just given by, as I said, it depends exponentially on what the value of the action is at the bound solution. And then there is some mass to the 4 scale in front, which basically depends on what the value of this determinant is. But basically, the scale that sets this mass is just the curvature scale of the potential around the barrier. Right, so the bound solution tells us about the decay rate, but it also tells us about what the bubbles look like when they are nucleated. So in particular, the bound solution is the initial boundary condition for what these bubbles look like. And later evolution of these bubbles is just obtained by analytically continuing the bounds. So in general, we want to know what these bounds look like in order to know what these nucleated bubbles look like. So in general, this is a complicated problem. Like the only way to solve this is just computing it numerically. But there is one interesting limiting case, which is the case of thin wall bounds. So thin wall bubbles or thin wall bounces arises in the case in which we have two vacua that are nearly degenerate. So the case in which the difference in energy densities between the two vacua is much smaller than the barrier height. And in this case, what happens is that the bounce looks something like this. So at the center, for r equals 0, the field gets to its true vacuum value, and it stays this for a while, up to a length scale that we typically call the critical radius of the bubble, and then it quickly changes to the value in the false vacuum. And if if the distance over which the field is changing is much smaller than the critical size, so the typical size of the bubble, if it's much smaller than 1, then we say this is a thin wall bubble or thin wall bounce. And then you should really think of this as when you nucleate the bubble, you have a region inside which is true vacuum. Then there is a very thin region around in which the field is quickly changing, and outside you have the false vacuum value. However, in general, when you have like a more general form of the potential, in which there is no obvious structure, then it's much harder to know. In general, it's not possible a priori to know how the bound solution looks like. And you cannot even tell whether, at the center of the bubble, when you nucleate it, you have the true vacuum or not. So this is a problem you need to solve for numerically. And in the cases we study, when we study the system very close to the appearance of this metastable vacuum, we always find what we would call thick wall bounces. Thick wall in the sense that, so this is the bound solution as a function of r, and here I'm just multiplying by some mass scale to make everything dimensionless. But basically the idea is that the typical size, the typical radius of these bounds is actually is comparable to the length over which the field is changing. So very thick walls in both cases. As you can see, I said before that the true vacuum value was psi equals pi. You can already see that this is much below pi. And in fact, the value of the field at the center of the bubble only evolves to the true vacuum much later as the bubble expands. So this is what we find in our case for how the bubbles look like. And regarding the decay rate, as I said before, in general the decay rate per unit volume has this form. For the value of the action evaluated at the bounds, we find an expression of this form. Just look at this last part here. So it's a numerical factor. It obviously depends on what the value of the string coupling is. But notice it depends very strongly on what the values of these fluxes are, in particular. And then this is some function of delta that we find numerically to be like this. But notice this, as delta is becoming smaller, so delta becoming smaller means the barrier is disappearing. then this becomes smaller, which means this whole thing is becoming bigger. So it becomes easier to nucleate bubbles, as you would expect. And then for this mass scale in the front, what we find is an expression of this kind. So there's some numerical coefficient in front, not very large, not very small. And basically this whole mass scale is actually set by what the characteristic energy scale of the throat is. So the fundamental scale, which would be the string scale, times this work factor. And then it also depends on delta linearly. Yeah, so this is parametrically what we find in these cases. Yeah, so as I said before, the picture is the following. So when this quantity, so this nucleation probability, becomes a further one, you start nucleating bubbles of true vacuum. And they are approximately spherical and at rest. And on average, you will find like one bubble in every Hubble volume. In the cases we consider, we find that this, the radius of these bubbles at the time of nucleation are much smaller than a Hubble length. And so the mean separation between them is over the Hubble as well. And then they start expanding, growing very fast. And in our case, I'll point later that this is actually quite different to what happens in the thermal case. They reach relativistic velocities very quickly. Right. Okay, but so as you nucleate these bubbles and they expand, the temperature keeps dropping, so this nucleation probability keeps growing. So now the question arises of how this transition completes. You could imagine this guy is growing so quickly that actually you nucleate many bubbles that are small. They don't have time to grow very much before they collide with each other. Or maybe this doesn't grow so quickly and then they have time to grow very much, and the way the transition completes is actually very few bubbles colliding. In our case, in which we are studying a zero temperature case for the hidden sector, what actually happens is that because this is not changing with temperature, this quantity is actually growing not very fast with temperature. So actually the way this transition comes to an end is by a few bubbles becoming large and colliding. Whereas in a thermal case, where this is exponentially dependent on temperature, you actually find yourself in this situation rather. Yeah, so this is just what I said. So in our case, this doesn't grow very fast. So we find that the typical time it takes for the transition to complete is a further Hubble time, in fact. And the temperature between, so this could be the temperature at collision compared to the temperature at which the nucleation starts, it changes by around 60%. Yeah, so in our case, the velocity of the bubble walls at the time they collide is very close to the speed of light. Is the limit of ultra-relativistic bubble walls. And the gamma factor also becomes very large. So, we have gamma factor for the 10 to the 4, which just basically means that, I said before that when these bubbles are nucleated, they have these very thick walls. As they expand and they become Lorentz contracted, actually this wall will become very thin. And so actually, the usual assumption that people make when they try to numerically simulate what a gravitational wave signal looks like from these colliding bubbles, so they assume that all the energy density is concentrated on the bubble walls, which is actually a good assumption in this case too. Even though you started with very thick walls, as they expand, they actually become thin. Right. Yeah, so let me emphasize some differences compared with a thermal first-order phase transition case. So in this zero temperature case, I told you that the bubble walls actually very close reach this ultra-relativistic limit. In the thermal case, however, you have a whole thermal plasma outside the bubbles that are interacting with them. And what typically happens is that this thermal plasma typically slows down the expansion, and it's actually much harder for the bubble walls to expand so fast. So typically what you find in these cases is velocities of order 0.1 or 10 to the minus 2 the speed of light.
Do you try to estimate, I could imagine that we could get unlucky and not have any bubble collisions in our Hubble volume. There's some probability for that.
Yes.
So it's because you seem to be saying, if I understood, that there's sort of not many bubbles within a Hubble volume. Is that, do you have an estimate of what that probability would be?
Yeah, so I mean, that's a good point. So the worry is that you could have like some Hubble patch in which you don't nucleate any bubbles.
Right.
And if at some point the vacuum energy density becomes dominant, then this would start expanding, right? And you would enter in a period of kind of exponential expansion everywhere. So that problem is solved basically, but yes, so that basically puts a bound on how much.
Sorry, I didn't mean that you don't have a bubble. I just meant that you have one bubble. You have exactly one bubble that then just expands and fills the whole Hubble volume. That's the scenario I was.
So where you don't have collisions.
Yeah, you don't have
So
collisions.
it's a failure mode for this scenario.
Well, you can have one Hubble volume in which you nucleate one bubble, that's fine. But the thing is that, at the time, the number of Hubble volumes at the time this is happening is many compared to what we have now. So I don't, even if there was at the time one Hubble volume in which there was only one, there's just another Hubble volume in which there are many.
I see, I'm sorry.
So actually it doesn't matter.
I got it.
Does that make sense?
Yeah. Okay.
Okay.
I got it.
Good. So the other difference, as I was saying before, is that, so as I said, in the zero temperature case, this probability of nucleation is growing very slowly. So this basically just means that the time it takes for the transition to complete is a further Hubble time. So this is a rather long time. Whereas in the case of a thermal phase transition, this quantity is actually growing very fast, and the transition takes much less time to complete. So they just basically mean that your source of gravitational waves, in this case, is on for a much longer time. And so these 2 points together actually make the strength of a potential gravitational wave signal much stronger in this case than it would be in a thermal situation.
So I didn't understand. You said that it makes it last longer. I thought you said that this thing completes in a Hubble time, where the Hubble is the Hubble when you first have this, right? When the bubbles first start happening, right?
Yes.
So,
Yeah, all I'm saying is that the time it takes to complete here is a further Hubble time,
right.
at this at the
that's longer.
Whereas this is much further.
Okay, got it.
So you are producing gravitational waves potentially over a much longer period of time.
But in the thermal case, you would have many more collisions, right?
You will have many more collisions, but they will only last for a very tiny fraction of time compared to this. Yeah, so I agree that those are kind of opposite effects. So it's not clear. Yeah, there will be some. I'm sure there are some cases in which even though this is true, the gravitational wave signal may become maybe stronger here. However, I think the most crucial effect is actually not this, but it's actually the velocity. So I'll mention it later, but actually the strength of the gravitational wave signal is at least goes like vq. So, even if you're 0.1 velocity, this is already so much weaker. Yeah, and then there's another important difference actually, which is in the zero temperature case, the main source of gravitational wave emission is the collision between bubble walls. However, in the thermal case, there are also other sources, like for instance, turbulence that's going on in the thermal plasma, sound waves, and so on. And actually, this typically tends to dominate over this type of source. And this actually has a different, the signal has a different shape. So it's actually very easy to tell these two things apart just by how the signal looks like. Yeah, so I don't know, I should have mentioned this. So, we have this picture of bubbles colliding everywhere at the time. So to us, this is going to look like a stochastic background of gravitational waves. Of course, the signal will have some peak frequency that will be set by what the size of the bubbles are. But just to think of there's some peak frequency, and then the signal also has some shape as it falls up with frequency. Yeah, so regarding the frequency of this gravitational wave signal, so these bubble wall collisions will lead to stochastic background. And the frequency peak that we'll see today is approximately given by this expression. All these factors will just come from redshifting to our frequency today. But basically this frequency is set by the size of the bubbles when they collide. And here, there's obviously a correspondence between the temperature of the visible sector when this is happening, when the collision is taking place, and today. The one thing I want to emphasize is that the temperature at which this is happening depends very strongly on what the details of the throat are. So as I told you before, we had this decay rate that depended exponentially on something like the fluxes I had around. So this actually depends very sensitive on the underlying parameters, say, of our throat sector. So you should think of this frequency as scanning over all possible values. As I change my fluxes and so on, it will change widely. So in particular, so this plot shows the frequency peak of this stochastic gravity wave signal as a function of the warp factor of one of these throats. And I'm showing this for 3 different values of the overall compactification volume. So for instance, so as this parameter delta, so remember the delta parameter is just telling us how far we are from the critical situation in which there is no barrier in the potential. So as I take this delta smaller, which means the barrier height is smaller, the frequencies are higher, which makes sense because if you're very close to the critical situation, you only need to draw the temperature a little bit for your nucleation probability to start becoming order 1. Similarly, as the volume of the compactification becomes larger, this basically means that the string scale is smaller, your fundamental scale is smaller, so you need to wait for a lot longer. You need to wait for the temperature to drop more for your nucleation probability to become order 1. So, but the upshot of this plot is actually that, the frequency of the potential signal actually covers a very wide frequency range, and in particular, a frequency range that will be probed by current and future gravity wave detectors. And all this requires actually is that there is at least one of these throats, of these very many that we expect to have, finding itself in this false vacuum with a value of delta in a suitable range, say. And of course, this is not something that is guaranteed, but maybe in a statistical sense, that doesn't seem unreasonable, right? And so that was about the frequency of the signal. Then the other important thing about the signal is, of course, its strength. So as I said before, this is going to be strong compared with the case what you would find in a usual thermal transition because it lasts for longer, so the source of gravitational waves is on for a longer time, and also because the bubbles quickly reach these ultra-relativistic velocities. So this expression just gives you roughly the strength of the gravitational wave signal, and here I'm already putting V to be 1. If I was keeping my factors of V, then I would find at least a suppression of V cube, as I said before. And then obviously, the longer, so this basically is the duration of the transition, and the stronger the signal. So just for illustration, this plot shows what the shape of the signal will be in terms of the energy density in gravity waves as a function of frequency for 3 different values of the frequency peak. Of course, the frequency peak could be anywhere. I've just chosen 3 of them just to show it. So there will be some peak of the frequency, and then it falls off with frequency on both sides. So these color regions here correspond to the maximally optimistic case in which the ratio of the vacuum energy density to the thermal energy density at the time of collision is 1. So that's the maximally optimistic case. As you take this number to be smaller, the peak will become smaller, as indicated by these lines, obviously, as you would expect. But notice that, so even for values of alpha of this ratio at collision, which are rather small, this is still within an observable range, at least in some of these experiments. So it's kind of potentially interesting. There's one thing I want to emphasize though. So strictly speaking, the shape of the signal is true if I had like a normal scalar field with normal kinetic terms and everything. So for instance, if I had a hidden sector that was like, not a string theory, nothing like that, then this would be the signal you would see. Actually, in the case I'm talking about, in which this field that actually has this weird looking kinetic terms because this is what brains do in this compactification. So this high frequency part of the signal is going to be different. This is actually not true. We don't know how it looks like because it's very hard to simulate numerically. But this high frequency part of the spectrum should be sensitive to the underlying details of the theory. And yeah, this has to do with this kind of Dirac-Born infill-like inertness for this scalar field. And so this, if this is worked out, this could be something that could help differentiate between these cases. So
that in that last plot, I should take one of those curves as being an example of a frequency spectrum. It's not just some population. It really is somehow the spectrum. It looks like that.
Yeah. So each one of these, the frequency peak, as I said, would be just set by the typical size of the bubbles. But then, the stochastic background has a shape to it with the.
And so in principle, the experiments can measure that. If they're within the range of sensitivity, they should be able to, at some level.
Absolutely. Of course, the first thing they see was the peak, but with enough time, they should be able to tell how this is falling. And for instance, these pulsar timing array detectors, so the signals these guys are going to see from supermassive black hole binaries are stochastic backgrounds, because there are so many of them they cannot detect. They cannot really tell where they're coming from. They only see stochastic background, and they know the shape. So this is something they can do.
In other words, somehow they would see this as some sort of constant. This would be something that would be always on. I'm just trying to.
Yeah, this is something that is always on.
That's always on, right? Yeah. So they just see this as some sort of noise or something they can't get rid of.
Yeah. So in some sense, this is similar to what the CMB is. It's something that you turn on your detector and it should be there.
And are they actually prepared to do that? I mean, I don't know much about this.
Yeah. So eLISA, for instance...
It's not that they're going to subtract it away or something.
No, they are not. And so, for instance, eLISA people, so the cosmology working group, this is one of the things that they are trying to optimize. So now, they are still trying to agree on what the final characteristic of eLISA will be. And, they take into account these things, like, the motivation for a phase transition in the eLISA region is, strong. So this will be absolutely one of the things that we'll be looking for.
Sorry, were you done with it?
No, I'm done, yes.
So I might have missed something you were just saying, but so the shapes look very like a really special signal.
Yes.
And then I'm reading the note in brown there, and so how much have you said, or are you going to say about what's characteristic in terms of the shape?
Yeah, so okay, good. So in the case of if I was just looking at the standard hidden sector that was having a transition at 0 temperature, this is what the shape looks like. Okay. Exactly this. Okay. And this is different from a thermal case, because in the thermal case, you have other things going on, like all this turbulence with the plasma and so on, and actually this typically has, in terms of the total strength, is similar, but the way it falls with frequency is lower. So actually, when you put it on top of this, this actually dominates. So for instance, you can also tell the difference between the thermal case and the non-thermal case is obvious by this.
So that's understood well enough that...
Yeah, so the difference between the thermal case and a non-thermal case like this, like a standard non-thermal case, is quite, it's understood and that's kind of standard. The thing we don't know, because as I said, it's very hard to simulate numerically and also analytically, we haven't made a lot of analytic progress yet, is, so in the case in which I'm talking about the hidden sector that's rather exotic in the sense that, it has these kinetic terms that are different, we know that this is going to be different, but we don't know how it's going to be different. So that would be nice to know, but we don't know yet.
So, I think this is a related question having to do with the way you're dealing with this as a stochastic background. Do you know, have you looked at the question of, in our past light cone, how many individual signals we should expect at a given strain? Because you said that it's relatively few, relatively large bubbles, but presumably colliding very far back.
Yes.
So there's a competing effect there. How far back it is going to determine how many of those collisions we see.
I mean...
Is it really stochastic, or is it
Well, the thing
Just
is, yeah.
5 individual signals that are somewhere in that plot.
No, it will be a lot more than that, right? The thing is, as far as this detector is concerned, the moment you have more than a few events, it already looks stochastic to them.
And you assume this is happening in the radiation area, so
yes, I mean,
in your model you've put it,
yeah,
so there's many.
yeah. So I mean, it
But
will be enough to make
that's
this stochastic.
presumably just to give you something concrete structured calculation. I mean, is there anything stopping us from imagining this happening
Much later?
a week ago or something?
Yeah, so actually everything comes down to what this ratio is, right? And for instance, we've restricted ourselves to, anywhere between the end of inflation and BBN. I mean, just
Right.
because, if you inject energy, this could be resolved in BBN. Obviously, for BBN actually it doesn't matter so much because, if this is like 10 to minus 3, for instance, it won't matter for BBN. If you're doing this at CMB times, then it will matter, then you will have to be more careful. So yeah, I mean, you could imagine this happening later, but obviously this ratio will be subject to constraints. And then obviously, the strength of the signal will go down accordingly. So probably you won't be able to see. Right, so yes, there are a few comments actually, caveats on what I've said that I think are very interesting just to finish. So as I said before, the high frequency behavior of the signal, will be different from the standard or there are other interesting things. So for instance, we say all the time, and people say all the time, that these nucleated bubbles are spherical. And this is true because, this bound solution is a spherical solution. And that's fine, but, at the classical level, that's okay. But when you compute, you're computing this path integral, and you're summing over an infinite number of paths, and the bounds is only one of them. So actually, what really is going on when you nucleate one of these bubbles is so the solution is roughly spherical, but then you have basically quantum fluctuations on top of these that will break the sphericity of the solution. So these guys will have some, typical non-sphericity size and also some typical relative velocity compared to other parts of the wall. And in the case of a non-thermal transition, this actually, this typical deviation from non-sphericity is, is of this size, so 1 over b to the 1/3. So b was the value of the action at the bounds. And if you remember, for our case, we were finding this b to be of order around 30 or so. So 30 to the 1/3 is actually not a particularly small number. So we're talking about deviations from the spherical case of maybe around 30%. And the crucial thing is, so these quantum fluctuations on the surface of the wall actually introduce a new length scale into the problem, apart from the radius of the bubble. And crucially, this is a new length scale that is transverse to the direction in which the bubbles are expanding. So even though, for instance, the bubble wall was Lorentz contracting, as the bubble was expanding, this new length scale won't. So it will remain whatever it was when it was nucleated. And it turns out actually that no one has thought very much. So this is something that we were very surprised about, but no one has actually thought very much about how these fluctuations evolve as these bubbles are growing. There are some papers by Catherine Fries and others a long time ago where they look at what happens in the case in which you have a normal scalar field and you're nucleating bubbles, and they actually found that some of these fluctuations can grow for a while, and then they freeze. But basically, they found that they could grow all the way up to having order of being like 40% of the size of the bubble. So actually becoming rather large. So it would be interesting to know more about this, because this could be actually a mechanism by which we're generating gravitational waves before the bubbles collide. So, and because the frequency will be defined by this new length scale, it could be rather different, perhaps much higher frequency. But in any case, this is likely to play a role in what the shape of the actual signal looks like at high frequencies. And also as well in the possibility of black hole production when bubbles collide. Great. Okay, so just to finish, we all know that gravity wave detectors will help save the future physics in the coming decades. in string theory in particular, it's possible that we may get signals of very different frequencies that may arise due to this process of vacuum decay, due to these throat sectors that have very different energy scales. So something like, a soundscape connected to this landscape of vacua that we have in string theory. And yes, more generally, I feel like this is an example of how these detectors might help us learn something about physics of the highest energies. Right.
So what about non-Einstein gravity?
What about non-Einstein gravity?
Is there any of that in your theory, and so can it be part of what you see?
So in this case, that's rather. So this is actually rather independent of that because. So the process of vacuum decay here. So I said before the bubbles when they are nucleated they are very tiny compared to Hubble. So actually gravitational effects actually don't play any role on this nucleation event, and they won't play any role either much later as these bubbles collide. So this is not something that will show up in any of this physics.
How much more confusing does it get if you have many different throats at which this is happening? You would then presumably get some superposition
Yes.
of those spectra. Is there any way of getting an estimate of what to expect, or of, first of all, a theoretical estimate of how many throats this might happen, and then an observational estimate of how you could separate that?
To the first question, if we did,
He
if there
said,
were...
first of all, for the theorist's point of view.
Yeah.
So first of all, if there were many throats in a situation like this, in which a process of vacuum decay was happening, what the signal would look like would be just one patch over the other. They would just be superposed, and you would hope that experimentalists are good enough to pull one from the other. As to the question of how many different throats we expect, this is a question people always ask, but I find it very hard to answer because, I could tell you something like, I'm taking this delta parameter to be between 100 and 1,000. So I could tell you something like, 1 in 100 or 1 in 1,000. But actually it's much more complicated. This comes down to, defining something like, a measure of how likely it is for me to have, this compactification with these fluxes. And, this is not something, I don't think no one is capable of answering that.
I just was wondering if there had been some progress on that since the last time. Okay.
So if you did see one of these things, what would be the range of possible explanations? This would be one explanation, right? Presumably a first-order electroweak phase transitions for some parameters would be another. Are there any optimistic cases where you could somehow say it'd be very hard for it to be anything else, or is this? Can you say anything about that?
Yeah. So if for instance eLISA saw a stochastic background that had this shape, then it would be 100% clear that it's not a thermal transition because, as I said before, the thermal case has a different power lowering frequency because.
And does that apply to the electroweak phase transition?
So if the electroweak phase transition, that would be exactly that example of a thermal. But because there are other things going on, like all this turbulence in the plasma and stuff, this could have a different power lowering frequency. So actually, one thing that would be easy to say is whether it's thermal or not. And if you saw something like this, I don't know of any other example of a signal that looks exactly like this. So all you could say at this point would be like, well, there's some hidden sector that is at zero temperature, or a very small temperature that is undergoing a phase transition.
And the fact that it's, from a very phenomenological point of view, the fact that the signal is always on would somehow lead you to think it would be some sort of a cosmological thing. Cosmological means it's happening everywhere.
I don't think so. Well, the thing is...
Is there other things that could...
Well, so for instance, in the first stages of LISA, probably, before they leave the detector on for a while. So for instance, they also look at, for instance, these black hole mergers, right? So the moment they have 5 different black hole mergers, to them this already looks like a stochastic background.
Do they have directional information?
Now they do, yeah. So with 3 arms, they will be able
They'll be
to.
having, so they could do some kind of isotropy if it's not just coming from the arms in our galaxy, it's
Yeah,
coming
yeah.
everywhere isotropically. It could be
Yeah, but what I'm saying is like it's not very hard for like a few point sources to look to you like stochastic background. So I don't think that would be, but it would be more like being able to measure the frequency shape at both sides of the peak. I think that would be the main thing.
Any more questions? If not, then let's thank our speaker again.